Swayam Prabha. Digital India. Educated India.
Good morning. We continue with our discussion on B-spline curves and segments. Previously, we had discussed the partition of unity property. The property said that the sum of all non-zero order P basis functions over the knot span Ti plus 1, Ti is the closed end and Ti plus 1 is the open end, is 1. So I had showed on board that the sum of n4 I plus 1, n4 I plus 2, n4 I plus 3 and n4 I plus 4 for values of t in between Ti and Ti plus 1 will be 1. In fact, you would notice that these are the only 4 non-zero basis spline functions over this knot span. Any other basis spline function, for example this red one over here or this red one over here, will be 0 over this knot span. So in a sense, B-spline basis functions within a subgroup add to unity, and not all B-spline basis functions add to 1, as we had seen in case of Bernstein polynomials. Let me mention the property again. The sum of all non-zero order k basis functions over the span Ti plus 1 is 1. Today, I'll try to give you a general proof. I'll try to show that the sum of k order k basis splines, which are n k I plus 1 t plus n k I plus 2 t plus n k I plus k t is equal to 1 for values of t in closed Ti plus 1 open. What we'll try to do is we'll first try to add two consecutive B-spline basis functions, which are n k j t and n k j plus 1 t. Now if you notice, index j starts from I plus 1, and index j plus 1 would end at I plus k. So this is the start and this is the end. We'll use the recursion relation to sum these consecutive basis splines and then go further from there. So n sub k sub j of t plus n sub k sub j plus 1 of t is equal to t minus tj minus k over tj minus 1 minus tj minus k times n k minus 1 j minus 1 of t plus tj minus t over tj minus t j minus k plus 1 times n k minus 1 j of t. This is the recursion relation corresponding to n kj And then all we need to do is index j to j plus 1 to get another recursion relation. So we have plus t minus tj plus 1 minus k over tj minus tj plus 1 minus k times nk minus 1 j t plus tj plus 1 minus t over tj plus 1 minus tj minus k plus 2 times n k minus 1 j plus 1 of t. Now concentrate on this term here and this term here. What do you observe? You would see that nk minus 1 j is common, and also the denominator tj minus k plus 1 is common. You might want to try adding these two terms together. What will happen to the numerator in that case? The numerator will become tj minus t plus t minus t j plus 1 minus k. If you realize, that is the same as the denominator tj minus tj minus k plus 1, and they would cancel out. What would be left will be n k minus 1 j t, which is right here. So we have the first term t minus tj minus k over tj minus 1 minus tj minus k times nk minus 1 j minus 1 of t, plus these two terms will add to give nk minus 1 jt plus the last term here tj plus 1 minus t over tj plus 1 minus tj minus k plus 2 times n k minus 1 j plus 1 of t. Now this is a result of two consecutive splines, nkj and nkj plus 1 added together. We still have to sum those k basis spline functions. Let me copy this result in the next slide, right here. Now if I perform the summation of all the k basis splines, what do I have? I have summation r going from 1 to k of n k I plus r of t, and that would be equal to t minus ti plus 1 minus k over ti minus ti plus 1 minus k times n k minus 1 I of t plus summation r going from 1 to k minus 1 n k minus 1 I plus r of t plus t I plus k minus t over ti plus k minus ti plus 1 times n k minus 1 I plus k of t. This might look a little confusing. Realize that the index j would start from I plus 1 and the index j plus 1 would end at I plus p. So you'll have the first term corresponding to j equals I, the last term corresponding to j plus 1 equals I plus k, and then you'll have k minus 1 terms getting added together. Let me go back. If you look at this expression over here, in the summation nkj and nkj plus 1, nk minus 1 j get added together. If I have, let's say, nk j plus 2 again getting added over here, correspondingly, like in the case of nk minus 1 j, we'll have something very similar in case of n k minus 1 j plus 1, and so on. And that is why these k minus 1 terms, they get added together. Now look at this term here, n k minus 1 I. What would be its value for t lying in between ti and ti plus 1? You guessed it right, it will be 0, because if you notice, nk minus 1 I has the last knot as ti. Likewise, what would be the value of nk minus 1 I plus k for t again in between ti and ti plus 1? Notice that the last knot is ti plus k, and the first knot is ti plus k minus k plus 1, which would mean the first knot is ti plus 1. Again, in the interval ti plus 1, this basis spline of order k minus 1 will be 0. So we are left with summation r going from 1 to k of nk I plus r of t as summation r going from 1 to k minus 1 now, n k minus 1 I plus r of t. In a sense, the summation of k order k basis spline functions gets reduced to the summation of k minus 1 order k minus 1 basis spline functions. We can use this observation to further reduce this result to summation r going from 1 to now k minus 2 n k minus 2 I plus r of t. We do not lose the generality when we reduce the summation from this one to this one. And we can keep on doing this further. Summation r going from 1 to k minus 3 of order k minus 3 basis spline functions, and so on up till we get summation r going from 1 to 1 of order 1 basis spline function, with the last knot as ti plus r. Clearly, r equals 1 here. So this is equal to n1 I plus 1 of t. And you would know that this order 1 basis spline function has the value 1 in the interval ti plus 1. So initially you must have thought that proving the partition of unity property would be difficult. That is not so. Let me continue with this lecture, which is number 27, and further discuss properties of normalized basis splines. This one pertains to the number of basis spline functions, the knots, and the degree. For number of knots as n plus 1, and the number of degree p minus 1 basis functions as n plus 1, m equals n plus p. In English, what does it mean? It means that if the number of order P basis spline functions is known, then the number of knots gets automatically known. Let me work this thing out for you on board. I had mentioned earlier that you should be comfortable sketching B-spline basis functions to be able to understand and work out these properties. So here we go. So we have, say, n plus 1 B-spline basis functions. Each of order P. Let's try to sketch them. We start with the knot T0. The first one we sketch will be nomenclated as NPP. So this knot here will be TP. The second one will start from T1. It will end at TP plus 1. This will be nomenclated as NPP plus 1. Likewise, the third one starts from T2, ends at TP plus 2, and has the name NPP plus 2. I can keep doing this. Remember that I have to have n plus 1 basis functions. These are 3 basis functions. The last knot corresponding to the third basis function is TP plus 2. Can you guess how the n plus 1th basis function will be standing over this parameter axis? Let me sketch this thing for you arbitrarily. Let me first nomenclate so that I'm sure this is the n plus 1th basis spline. This would be n order P plus n plus 1. Is that the case? Now let's analyze this again. For the first B-spline function, I have the last index as P. For the second, I have P plus 1. For the third, I have P plus 2. For the nth basis spline function, I should have the index P plus n minus 1. And therefore, for the n plus 1th, I should have the index P plus n. I have to be very careful in working with these indices. Now, what would be the last knot over which NP, P plus n will be standing? You guessed it right again. This is T, P plus n. Start counting the number of knots. T0, T1, T2 up till Tp plus n. These will be P plus n plus 1 knots in all. And so, if there are m plus 1 knots, they have to be equal to p plus n plus 1, which would imply that m equals p plus n. This one is a slightly different argument for the same property. Now, if you're looking at the knot span T0 closed, Tm open, the first normalized spline on this knot set is npp of T. The last spline on this set has to be npm of T. Clearly, because T sub m is the last knot in the span. Now, these, if you count, will be m minus p plus 1 basis splines. Now, since we have n plus 1 basis splines already, n plus 1 has to be equal to m minus p plus 1, which would give us the result m equals n plus p right here. Let's now discuss multiple knots. It's a very interesting concept, and today we are going to be discussing this concept at a bit of length. The concept helps designing B-spline curves in a variety of ways. I'll come to that maybe in the next lecture or so. First, what is a multiple knot? If a knot Ti appears k times, that is, if Ti minus k plus 1 equals Ti minus k plus 2 equals, and so on, up till Ti, where k is greater than 1, then Ti is termed as a multiple knot, or to be more precise, a knot of multiplicity k. For k equals 1, Ti is termed as a simple knot. As I mentioned earlier, multiple knots can significantly change the properties of basis functions and are useful in the design of B-spline curves. We'll see this later. First, let's look at the graphics as to what happens if I use multiple knots. This is an important observation. At a knot I of multiplicity k, the basis function npi of T is Cp minus 1 minus k, continuous at that knot. Now, let's pause for a while and try to understand this. For simple knots, that is for k equals 1, an order p basis spline function has to be Cp minus 2 continuous everywhere. Now, if you plug in k equals 1 here, we get the result Cp minus 1, which is Cp minus 2 continuous, and that is for simple knots. Now, if I have two knots at the same position on the T axis, what would this statement physically mean? It would mean that I would lose the continuity of the curve at that junction point by 1. For example, if k equals 2 at a knot, then the basis spline Cp minus 3 continuous. If k equals 3, then at that knot, which has multiplicity 3 now, the function will be Cp minus 4 continuous. So I'll keep on losing the continuity conditions one by one if I keep on increasing the multiplicity of a knot. Here is an example of a quadratic basis function with Ti as the last knot. Here I is equal to 3. Now if you notice, we have 4 simple knots. In a sense, 3 knot spans. And this is how N3, 3 of T looks like. If I move knot 2 to the right, what happens to the shape of the basis function? We'll come to that in a while. Let's first analyze or observe that this basis function is C1 continuous throughout. It has slope continuity here, slope continuity here, and slope continuity throughout. Now once I have moved this knot to the right, the curve in red depicts the shape of the new basis spline function. Notice what happened here. I lost the slope continuity. If I further move knot 1 to the right, making the multiplicity of knot 3 as 3, the green one shows the new shape. Now we have lost the position continuity. Realize that we have a jump in position right here. The effect is similar when knots are moved to the left. The same function in 3i, T0, T1, T2, T3 as my 4 knots. This is the original basis spline function, quadratic. If I move T1 to T0, making T0 of multiplicity 2, I lose slope continuity here. If I further move T2 to T0, I lose position continuity further at this knot. Why do you think this would happen? Why is it that if we increase the multiplicity of a knot, we tend to reduce the continuity conditions at that knot one by one? We'll discuss this in the later part of this lecture. For now, at each internal knot of multiplicity k, the number of non-zero order p basis functions is at most p minus k. We can see this graphically. We have the knots Ti minus 7, Ti minus 6, Ti minus 5, Ti minus 4, Ti minus 3, Ti minus 2, and Ti minus 1. Let's concentrate on this knot here, Ti minus 4. And let's try to build B-spline basis functions around it. Can you guess how you would name this B-spline basis function? Right, N4 I minus 1, because it is turning over 4 knot spans with the last knot as Ti minus 1. Now I have sketched n for I minus 1 in such a way that this is non-zero over Ti minus 4. Let's try to sketch the other spline functions. This one here is n for I minus 2. This one here is n for I minus 3. Now this example is a particular one of this generalized statement. Here P equals 4 in our case. If you realize for Ti minus 4 to be a simple knot, non-zero splines over this knot is equal to P minus K, which is 4 minus 1, which is 3. N for I minus 1, N for I minus 2, and N for I minus 3. If I move Ti minus 3 to Ti minus 4, one of them now becomes 0 over Ti minus 4. Now with Ti minus 4 having multiplicity 2, we have P minus K equals 4 minus 2 equals 2 non-zero splines over Ti minus 4. If we move Ti minus 2 to Ti minus 4, another one disappears. We are left with only one non-zero basis spline. And finally, if I move Ti minus 1 to Ti minus 4, we are left with 0 basis spline functions which are non-zero over Ti minus 4. You would notice that the multiplicity of this knot is 4 now. Now let's come back and try to understand why do we lose continuity conditions one by one at multiple knots. I'll use the board to discuss this. I would like you to recall our discussion on polynomial splines. How did we construct a B-spline basis function using polynomial splines? Let's try to construct an order 4 basis spline function. Let me start with T0, T1, T2, T3, T4. I will need 4 knot spans. This is the parameter axis, T to the right and to the left. My B-spline basis function will start from T0 and end at T4. Again, I'll have to be careful with regard to the continuity conditions both at T4 and T0. Let me name these segments: phi 0, phi 1, phi 2, and phi 3. Each phi is a pure cubic polynomial. I can write phi sub I as ai plus bit plus ci t squared plus di tq. I would go from 0 to 3. If you realize, in all, we have 16 unknowns. 4 coefficients in each cubic polynomial. Now, if you remember, we started off with some conditions here and some conditions here. Specifically, we said that phi, the slope, and the second derivative are 0 here. Likewise, the position, the slope, and the second, this is the slope here, the second derivative are 0 at T4. Also recall that we had mentioned that the area under this curve, that is integral from T0 to T4 of phi t dt. Phi of t is a set of phi 0, phi 1, phi 2, and phi 3. This is equal to 1 over 4. 4 is the order of this spline function. So these are 3 plus 3 plus 1, 7 conditions. How about the rest of the conditions to be able to determine all 16 unknowns? Recall that we had used position, slope, and second derivative continuity conditions at this junction point, at this one here, and at this one here. So these are additional 3 plus 3 plus 3, 9 conditions. 9 plus 7 would be 16 conditions required to determine 16 unknowns overall. Now, this is something that you have known from before. Try to now guess what will happen if I move not T1 to precisely lay over not T2, making T2 a multiple knot of multiplicity 2. There is another way I can argue. If you realize you would need n plus 4 conditions, is this n plus 4 or n plus 3? You might want to check it out. N plus 3 conditions to completely and uniquely determine a spline function. Here n would be the number of knot spans. In this case, it is 1, 2, 3, 4. And we have 7 conditions. 3 plus 3 plus 1. Now, if I move T1 to precisely lay over not T2, think about it, that I tend to lose 1 knot span. In a sense, though initially n was equal to 4, after I have moved T1 to T2, n becomes equal to 3. Implying now that I would need 6 conditions. But I have 7 of them. 3 plus 3 plus 1. Clearly, I'll have to lose one of the conditions. Now moving T1 to T2, I would presume would not affect anything here around T0, or for that matter, anything here around T4. So I don't think it's a good idea for me to lose any of these three conditions right here, or any of these three conditions right here. I cannot let go of this condition as well, because this ensures non-zero area under this curve. Maybe I'm not doing this thing right. So let me step back and look at this problem from the point of view of these coefficients. For phi 0, let's say I have coefficients a0, a1, a2, a3. After I have snapped this knot span, I would not know what phi 1 is, and let me not worry about it at this time. Let me rather jump to phi 2 and say the coefficients of phi 2 are b0, b1, b2, and b3. For phi 3, say the coefficients are c0, c1, c2, and c3. In a sense now, these are my 12 unknowns. Let me start from T0. These three conditions will let us or allow us to express any of these three coefficients in terms of the fourth one. In fact, phi 0 will be equal to a3 t q. Let me ignore phi 1 for now and jump to phi 2. I have C0, C1, and C2 continuity conditions here initially. If I use these continuity conditions, I would be able to express three of these in terms of, say, B3 and A3. So by the time I come here, I will have two unknowns. Now if I work with phi 3 further, by the time I come here, I will have three unknowns. C0, C1, C2, using these three conditions, can be expressed in terms of, say, C3, B3, and A3. So by the time I reach T4, I'll have A3, B3, and C3 as unknowns, and I'll have three conditions to greet them. Well, how about this condition? I will not be able to use it. Let's go back. At this junction point, say if I let go of C2 continuity condition, if I do not use it, will I be able to compute my basis spline function? If I think about it, maybe yes. I start with A3 as unknown here. A0, A1, A2 are all 0. I come to T2. With only these two conditions, I will be able to express two coefficients in terms of the other two coefficients. In a sense, two of these coefficients will be unknowns. Let's say B2 and B3. Here A3 is unknown. And if I go on further, and if I use all three conditions, I'll have one more unknown by the time I come to T4. Now we have 2, 3, 4 unknowns and 3 conditions here, the fourth condition here, which is solvable. Now the question you would want to ask yourself is, why is it that I have decided to let go of the C2 continuity condition at this junction point, where we have not multiplicity of 2? I'll ask you to keep an open mind here. Although I had suggested that we can let go of this C2 continuity condition at this junction point, but maybe you can also think of letting go of one of these conditions, maybe one of these conditions, or maybe one of these conditions. It doesn't matter. Mathematically, all you need to do is ensure that you have the number of conditions the same as the number of unknowns to be able to solve for this B-spline uniquely. Let me pose an open question for you to mull on. Why is it that it makes sense for us only to let go of this condition? And why not any other? We'll discuss this in the next lecture. But before I leave, let me give you an assignment. Let's construct a quadratic normalized spline over this knot span 0, C, and this value is smaller than 1, 1, and say 2. We have T extending to both right and left. Let's say this is our quadratic normalized spline, or spline in general. Doesn't need to be normalized. Divide this into 3 segments: phi 0, phi 1, phi 2. Now, since this is quadratic, you need to be a little careful. You need to ensure that position and slope are 0 at the starting knot, and position and slope are both 0 at the ending knot. Now, these are 2 plus 2, 4 conditions. And the fifth one is integration from 0 to 2 phi t dt equals 1 over 3. 3 is the order of quadratic spline. So you have 5 conditions. So this is what the idea is. We are trying to do an experiment. We are trying to construct quadratic normalized spline with arbitrary value of this knot here, C, which is smaller than 1, so that C happens to be a simple knot, and these are simple knot spans. And once we get the expressions for phi 0, phi 1, and phi 2, we will let C tend to 1, so that this knot here becomes a multiple knot, and observe what happens to this quadratic spline overall. Let's meet next with the solution to this problem.